Hello everyone, welcome to my tutorial video on travel graphs. So today I'm going to take you through displacement and velocity. Displacement is defined to be the change in position of an object in a given direction, and it can be defined by the following equation. Delta x is equals to xf minus x naught, where xf is the final position, x naught is the initial position of the object, and delta x is the symbol that is used to represent displacement. You need to note that displacement is a vector. It has a magnitude and a direction. So now looking into displacement time graphs. Displacement time graphs show how the displacement of a moving object changes with time. So for example, in the graph that is given above, the displacement of the object after 7 seconds can be read off from the y-axis to be 20 meters. And a few points to note about displacement time graphs. The gradient at any point of a displacement time graph is equal to the velocity, where velocity is defined to be the rate of change of displacement, and also the steeper the line, that is, the greater the gradient of the displacement time graph, the faster the object is moving. So since we said that the gradient of a displacement time graph gives us velocity, it implies that if the gradient is greater, the larger the velocity, that is, the faster the object is moving. So you also need to note that the area under the displacement time graph has no real meaning. And then also, you need to note that a horizontal line on the displacement time graph shows that the object is stationary, that is, the object is not moving. So for example, in the graph that is shown on the screen, the object remains stationary at 15 meters, that is, it is not moving. Okay, so now we're going to look at an example of how to draw displacement time graphs given a description. So you might as well need to pause the video and work through the question and then continue after you have your solution. So one thing that is important is that you break the question into components that you understand, that you can deduce from the question. So we know that between 12 and 1:30, nearly traveled from 0 kilometers to 44 kilometers away, and between 1:30 and 4:30 he was in one place, he wasn't moving, and between 4:30 and 6:30 he traveled from the 44 kilometers back to 0 kilometers where he had started from. So if we are to draw the displacement time graph, it's something like this. So this is the first segment, like between 12 and 1:30. We see that he was moving. We say that he was moving with a constant velocity. We say that because if you were to calculate the gradient at any point on this graph, you'd get the same gradient. So this means that he was moving with a constant velocity. And then the next segment, that is the next 3 hours, he wasn't moving. Thus we have a horizontal line, and this is the 44 kilometers that can be read off from the y-axis. And then in the last segment, that is the last 2 hours of the journey, he moved from the 44 kilometers back to 0 kilometers where he started from. So the graph that you drew should look like this. And then now we'll look into velocity time graphs, but we need to understand what is velocity. So velocity is defined to be the rate of change of displacement and can be defined by the following formula: velocity is equals to displacement over time. And a few points to note about velocity time graphs is that velocity time graphs show how the velocity of a moving object changes with time. And the positive gradient of a velocity time graph is acceleration. And the steeper the line, or the greater the gradient, the greater the acceleration. So again, since we say that the gradient of a velocity time graph gives acceleration, it means that if the gradient is greater, then the acceleration is also great. And then a negative gradient on a velocity time graph tells us that the object is decelerating. And we define acceleration to be the rate of change of velocity, and is given by the formula: acceleration is equal to final velocity minus initial velocity over the time taken. And you need to know that the area under a velocity time graph gives the distance traveled in a specific direction. So now we are going, okay, so now this is a general representation of a velocity time graph. So you just understand it's a random graph. So the red line, it gives us acceleration, and it's a constant acceleration because if you're to calculate the gradient at any point on the graph, you'd get the same gradient, which implies that it's a constant acceleration. And then the blue line, it's a horizontal line, and this means that the object is traveling at a constant velocity of 3 meters per second. You need to note that this horizontal line does not mean that the object is not moving. No, it means that the object is moving, but its speed is not changing with time. And this black line shows that the object is accelerating, but the object is accelerating. The acceleration of this part is greater than the acceleration of this part, because if you're to calculate the acceleration of the gradient of the black line is greater than the gradient of the red line. So we can deduce that the acceleration for this black part is greater than the acceleration of the red part. And then in the last segment, we say that the object is decelerating because if you're to calculate the gradient at any part of the graph, you'd get a negative gradient. So a negative acceleration, like we said before, gives us deceleration. So now we are going to look at an example that has to do with velocity time graphs. So below is a graph that shows a car that is accelerating from rest. And part A, we are asked to find the acceleration in the first 10 seconds, and part B asks us to find the acceleration in the last 20 seconds, that is between 30 seconds and 50 seconds. So looking into part A of the question, which asks us to find the acceleration in the first 10 seconds, we know that acceleration is given by the gradient of the velocity time graph, and it's given by the formula final velocity minus initial velocity over the time taken. So we can read off the final velocity from the graph at this point to be 40 meters per second, and the initial velocity to be 0 meters per second. So substituting those values into the equation, we have 40 meters per second minus 0 meters per second, the initial velocity, divided by 10 seconds, that is the time taken to increase to the speed, the final velocity, 40 meters per second. So if we work through, we get 4 meters per second squared as the acceleration during this time. And then moving to part B, which asks us to find the acceleration in the last 20 seconds of the journey, that is between 30 and 50 seconds. Again, we use the same formula, which says that acceleration is equals to the gradient of the graph, and it is given by velocity, final velocity minus initial velocity over the time taken. So now we read off from the graph. We are mainly concerned with this segment because that is where we have the 20 seconds, like between 30 and 50 seconds. So we note that the final velocity in this case is 0 here, which we read from the y-axis, and then the initial velocity where it started from at the 30-second mark is 60 meters per second. It can be read off from the y-axis. So substituting the values into the equation, we have 0 meters per second minus 60 meters per second. So 0 meters per second is the final velocity minus 60 meters per second, the initial velocity, divided by 20 seconds, which is the time taken to change its velocity from 60 meters per second to 0 meters per second. So working through, we get the answer to be negative 3 meters per second squared. So the answer is negative, and from this we can conclude that the velocity of the object is decreasing per unit of time, and this is what we call deceleration or retardation. So you might choose to write the answer as the car has an acceleration of negative 3 meters per second squared, or the car has a retardation of 3 meters per second, or someone may choose to write it as the car has a deceleration of 3 meters per second squared. So now we are going to look at drawing velocity time graphs given descriptions. So shown on the screen is a question that we have to go through, and it reads, A ball is placed at rest at the top of a hill. It travels with a constant acceleration for the first 12 seconds and reaches a velocity of 4 meters per second. It then decelerates at a constant rate of 0.1 meters per second squared for 20 seconds. It then travels at a constant velocity for a further 18 seconds. And so we are asked to draw a velocity time graph for the ball over the course of this 50 seconds. So you might as well need to pause the video, think through the question, and draw the velocity time graph if you manage to. So like we did in the case for the displacement time graph, you need to break the question into different segments that you can understand. So you get the segments from the question. So in this case, we are going to deal with the first 12 seconds of the journey. So what we know about this first 12 seconds is that the ball was moving with a constant acceleration until its velocity was 4 meters per second. Right? So this means that since it's a constant acceleration on a velocity time graph, it's a straight line, and this straight line is going to move from the point coordinates of 0, 0 to 12, 4, where 12 is the 12 seconds and 4 is the 4 meters per second. And then next, we know that the ball for the next 20 seconds, it was decelerating at a rate of 0.1 meters per second. What this simply means is that the velocity of the ball was decreasing by 0.1 meters per second every second. So we can then calculate the velocity of the ball after this 20 seconds by saying 0.1 times 20 to get 2 meters per second. So we note that during this 20 seconds of the journey, the velocity of the object decreased from 4 meters per second to 2 meters per second. And we also know that it was decelerating at a constant rate. So again, on a velocity time graph, a constant deceleration is a straight line, but then this time around, the straight line is going to have a negative gradient. All right. So this means that the line that we are going to draw is going to be a line that will start from the point coordinate 12, 4 to the point coordinate 32, 2. And then lastly, in the last segment, in the last part of the journey, that is the last 18 seconds, we know that the ball was traveling with a constant velocity. So from what we learned that a constant velocity is a horizontal line on a velocity time graph. What this means is that the velocity of the object is not changing per unit time. So thus we draw a horizontal line until the 50-second point. So if you're to draw the graph, it should look like this. So this is the first segment of the journey, the first 12 seconds. As you can see, it's a straight line from the point 0, 0 to the point 12, 4. This point is 12 seconds here on the x-axis. So if you are to calculate the gradient at any point of the graph, you note that you get the same gradient. And from what we learned that if the gradient is the same throughout the line, it means that it's moving with a constant acceleration. And in this case, the acceleration is positive. And then for the next segment, that is from the 12 seconds to 32 seconds, this mark here is the 32-second mark. We were told that from the calculation that we did, we noted that the velocity of the object decreased from 4 meters per second to 2 meters per second. The 2 meters per second can be read off from the y-axis here. So since we said that there is a decrease in the velocity, it means that the object was decelerating, right? So this also can be proved by the fact that if you are to calculate the gradient at any point of the graph, at any point of the segment, you will get the same gradient, and the gradient in this case is going to be negative, and the negative gradient on a velocity time graph shows that the object is decelerating. And now we look into the last segment of the journey, that is the last 18 seconds of the journey. So from the question, we were told that during the last 18 seconds, the object was moving with a constant velocity. So what this means is that the velocity of the ball was not changing per unit time. So it moved with the constant velocity for the 18 seconds till it reached the 50-second mark. So I hope the graph that you drew looks something like this. Take some time to understand the question and go through it again. I hope you found this helpful. Thank you for watching my video. See you again in the next video.